What I'd like to do today, gents, is to go through the graph which you drew last time, and the data for your graph came from dropping drawing pins on the table, you will remember. Those that land on your backs, on their backs, I beg your pardon, you're thought of as being the ones, the nuclei that are staying stable, that aren't decaying radioactively. The ones that land on their side, you said, well, they're like the ones that have given out an alpha, beta or gamma, so we're going to take them out of the game, and hopefully what you got was a graph something like this. Okay, you should have some sort of curve looking a bit like a sort of ski slope kind of thing. Up the side, if you remember, we plotted the number left undecayed, all right? So as the number goes down, this is obviously the number of nuclei in your sample, and it goes down and down and down as more and more nuclei decay by radioactivity, okay? On the bottom, we kind of had time, although we didn't measure it in seconds, we measured it in the different numbers of goes that we had tipping the drawing pins on the table, okay? You should have got a curve looking something like this, and that's unusual in GCSE physics. Most of the graphs that you come across in GCSE physics are straight line graphs, all right? If you've ever wondered what bits of physics are in GCSE and which bits aren't, it's often to do with the fact they give a nice friendly straight line. For example, you've all drawn a graph of voltage against current, and you will have got a straight line, okay? And that's famously known as Ohm's law, and the gradient of the voltage current graph is equal to the resistance, okay? Good thing about straight lines is that you can obviously use their gradients, as you don't need to be told. A straight line graph has a constant gradient. I can say this line has a gradient of 20, and because it's a voltage current graph, that 20 means the thing that produced this has a resistance of 20 ohms, okay? I can draw a graph of distance against time. I can measure the gradient there being 20, and that means obviously if you draw a graph of distance against time and you get a gradient of 20, it means the object was travelling at 20 metres per second. If it was a velocity time graph, that would mean it had an acceleration of 20 metres per second squared. So an awful lot of the physics that we do is about getting straight line graphs and using their gradients. And of course, the good thing about the gradient of a straight line is it's the same all the way along. Okay? Let me suggest to you then that this curve was an actual hillside. Think of it like it was a hillside. And imagine I gave you a whole load of gradient signs like 1 in 10 or 50% or something like that. And I told you to go along and to put the gradient signs up for motorists who want to drive up this hill. I think you'll see what the problem is. Down at the bottom, if you put the gradient is 10%, it's fairly shallow, sort of 1 in 10. When you get to here, it's nothing like that. It's much, much steeper, 1 in 4 or 25% or something. So this is a bit of a problem because we can't use the idea of gradient. And as I said, if you look back through almost all the physics we do at GCSE, it's about things having a constant gradient. Pretty obviously, this curve does not have a constant gradient. It's very steep here, that means a big gradient. It's fairly flat there, which means a low gradient. It's nice to be able to look at a line and say 20, resistance of 20, speed of 20, something like that. We obviously can't do that with this curve. Trying to label this hillside with a gradient sign would be really difficult. Each of these you can just put 1 in 20 or 5% or something like that, and it would be true all the way up the hill. Okay? This one, I think you can see the gradient is changing all the time. Okay? Now, what I need you to think about is how we get round this, all right? The particular curve you've got here is called an exponential curve. And I've heard some of you use that word in the past to describe graphs when it's not appropriate, all right? This is a very special kind of curve in maths. It's called an exponential curve. It might just look like any old curve to you, and the one I've drawn on the board most certainly is, but if you look in your graph that you drew for yourselves, the important thing is, and the link you need to make in your mind, is that the process you did last time with the drawing pins was a random process, okay? You were chucking the drawing pins, you had no way of knowing which ones would land on their sides and be radioactively decaying and which ones wouldn't. It was a random process. We could do the same thing with dice. We could get dice out and take all the 6s out, throw the rest, take all the 6s out, throw the rest, take all the 6s out. You would end up with exactly the same shape. So get this link in your mind. When there's a random process, you end up with an exponential curve. If you were wondering last week why you did a silly experiment with drawing pins when we're meant to be doing nuclear physics, The answer is if we got some radioactive nuclei and we counted them, and then we measured a second later how many are left, and how many are left, and how many are left, we would get exactly the same shape. And importantly, it would be a special type of curve called an exponential curve. Okay? Now, exponential curves obviously don't have a constant gradient. The gradient's changing all the time. But they do have something which stays the same all the way along. Okay? It's obviously not the steepness, which goes from big down to small. But there is a property of an exponential curve which is the same all the way along. Okay? And that's why it's such an important curve. And this is something you can do. I'll ask you to look at this for homework. This is something you can do with your curve, and it'll probably give you the right answers. I'm going to sort of estimate it on the board, but you've got the correct shape on the piece of graph paper in front of you. Okay? Let's suppose you started off with 100 nuclei, or 100% or something. Unfortunately, you will have started with some abysmal number like 385 or something like that. And let's suppose I measured how long it took to halve. Okay? So I'm not going to measure how much up for how much along, your traditional gradient thing, because obviously that's not going to work. But if I measure how long it would take for the number to halve, and the easiest way to do that is to start with your starting number, work out how many is half of that. I started with 100, so that's nice and easy. I can go to 50. And the time it takes to do that has a special name, has a special symbol, capital T with a little subscript half. You can add that to your graph. And its posh name is, it's called the half-life. All right, and I hope you've already measured the half-life of your curve. But it's basically, as you can see, as it says on the tin, it is the time to halve. It's not the time to go down by a certain amount. Let me show you that, because I could also measure the half-life if I wanted to. I could measure it by going to 25. I could say, well, I'm not going to start at 100, I'm going to start at 50, and I'm going to go down to 25. And that, again, would be halving, all right? Can you see how it's different to your normal gradient? Normal gradient says for every foot you go along, you go 3 feet up, or something like that. For every second you go along, you go an extra 20 metres. It's a certain amount of distance or time or something along the axis. Here we're not doing that. I'm not saying how long does it take to go down by 50. I'm saying how long does it take to halve, all right? Which is a different kind of thing. It's not specifying a certain amount. Here, halving means dropping by 50. And here, halving means dropping by 25. And if I'm getting ambitious, if I do it again, this one's worked out quite well actually. If I do it again, halving, down here, halving means going from 25 to 12.5. Okay? Now, that's a really important idea. The thing we're going to measure about this curve is not its gradient, but its time to halve. If you want a definition of half-life, that sounds a bit dark, but you literally just swap the words around and turn it into a verb. No such thing as time to half. The time to halve, all right, an unusual thing to measure because it isn't saying how long to go down by 20 or how long to go down by 50 or something. And as you can see, if you start off at 100, halving means dropping by 50. If you start at 50, halving means dropping by 25. And if you start at 25, halving means dropping by 12.5. All right? If I did it on these curves, I'd get different numbers. Okay? But what you can notice, even from my rubbish drawing, you can hopefully notice what's happening. This first half-life that I measured was a drop of 50. When I said let's do half-life from 100, that means dropping by 50. And that's a big drop, but look, the curve is very steep. Down here, halving means only dropping by 12.5. But at this part of the curve is now very flat. And it's those two things that exactly cancel each other out. There's only one curve in maths where that's the case, and that's the exponential curve. It has the special property that the amount you're going down and the flattening of the curve, the two things exactly balance. And even with my terrible drawing, you can see that the half-life stays the same. Okay? Time to halve at the beginning means a big drop on a steep curve. Time to halve towards the end means a small drop, but on a flat curve. Okay? And the important thing to notice, and the thing I'd like to do on yours, is just to put your half-life and a great big arrow all the way down your curve. This is the one thing you need to take away from half-life. It's the same everywhere along the curve. All right? Everywhere you go along the curve, the time to half will be the same. Think about our gradients and our straight line graphs from lower down the school. What was nice about them is it's got a gradient of 20 ohms everywhere, all the way along, all the way along, just like a hill that goes up at a constant gradient. It's the same everywhere. There is a number that stays the same everywhere for this curve. All right? It's not so obvious as the gradient on a straight line. That's obviously the same all the way up. There is a number that's the same all the way along this curve. It's not the time to drop by 20. It's not how much do you drop for 2 seconds along. It's how long does it take to halve. So the key thing, gents, is anywhere along this curve you would get the same half-life. The time to halve is the same everywhere along the curve. Best way to do that would be to put a line all the way along your curve. All right? These are obviously lines of constant something. Even year 10 can spot that. But this is a line of constant something as well. It's a line of constant fraction. All right? It doesn't go up by the same amount each time. Imagine walking up it, you can tell that. But it does take the same amount of time to halve. All right? Wherever you measure half-life along here, then you would get the same answer. Okay? Can you make that really clear, please, on your graph? Because that's the key idea of half-life. All right? Can we just add in, because people sometimes get muddled with these, the examiners will obviously ask you to do a bit of maths with this. They'll ask you to calculate how long for this to happen or whatever. And it's useful just to jot down a little table. So can you just jot down a little table of number of half-lives? And we don't need to go very far with this. Let's not do more because that's stupid. You only need, I reckon, to go up to about 4. Exam questions don't really go much above 4. Okay. And here we can have number left undecayed. Okay. There are no prizes for guessing. If you wait for one half-life, how many atoms will be left? We don't know. Depends how many you started with. Okay. But we do know that you will have half of what you started with. Okay? Instead of saying a certain number for a certain number along, this always talks in terms of fractions. So whatever number you started with, if you wait for one half-life, if they say this nucleus, the half-life is 6 days, it doesn't matter how much of the material you've got. You could have a tiny, tiny speck of the material. You could have an entire, 5 tons of it. If you wait for 6 days, half of it will have decayed and turned into something else. Okay? Now, if you wait for 2 half-lives, again, think about it. It's halving. If I say the half-life of this material is 6 days, that means every 6 days it's halving. That doesn't mean it's going down by half. Are you with me? So if you started with 100 nuclei, doesn't mean it's going down by 50 every time. The first time you do halving, that did mean 50, but the next time it'll only be 25. It'll still be halving. So hopefully you can jot down then. It's a quarter. If you wait for 2 half-lives, then you'll be down to a quarter. Okay? And this is where people's brains immediately lock into the 2 times table. 2, 4, 6, 8, 10. But of course it's not. If you wait for 3 half-lives, I hope you're clever enough to spot, it's going to be an eighth. Think about it. Half, quarter, it's not 6, it's eighth. And then the next one would obviously be 16. Okay? And if you went on 32, 64, 128, etc., etc. Okay? It's dividing by 2, which is a binary thing. Computers, as you know, are binary things. They just have noughts and ones. They work on powers of 2 as well. And that's why if you carry this on, you get to numbers of bits and stuff. You'll recognise 256 and 512 and stuff like that. Okay? Occasionally, just to confuse you, let's just squeeze an extra column in. Okay? What I could do if I was a meanie is I could mention this. Sometimes exam questions say to you, a student waits for a certain amount of time and discovers there's only an eighth left. And it took 30 days. So a student waits for 30 days and finds that they're left with only an eighth of what they started with. And what you're meant to do is say, oh, look, an eighth, I recognise that. An eighth means 3 half-lives. How long did it take her? 30 days. Well, if 30 days is 3 half-lives, the half-life must be 10 days. Okay? But sometimes, to muddle you around, what they do is they tell you how much has decayed. All right? Not left undecayed. So I could obviously do it the other way round. It could be half, it could be 3/4, 7/8, and finally 15/16. If I was a bit of a meanie, I could say, well, 7/8 of the material has decayed. You're thinking 7/8, I remember that, half, quarter, 8, 16, 7/8. Think about it. If 7/8 has decayed, what's the question really telling you? It's telling you you're only left with 1/8. So I know this is pretty simple stuff, but just make sure you've got those written down, okay? So after 1 half-life, it's a half, 2 half-lives, a quarter, 3 half-lives, you'd have an eighth left, and after 4, if you cut a cake in half 4 times, you're left with 16ths, okay? And watch out for questions that either tell you what's left undecayed, or they tell you how much has decayed, all right? Make sure you can flip between the two nice and easily, okay?